In the spring of 1992, the Endeavour space shuttle stood poised on its launch pad at Cape Canaveral, Florida, ready for its maiden flight. The crew, including astronaut Bruce Melnick, was aboard, preparing for a daring mission, a rendezvous between two spacecraft in orbit to rescue a stranded satellite. This satellite, stuck in a useless 800-mile-high orbit due to a failed rocket stage, was never meant to be handled by human hands. Its intended destination was geosynchronous orbit, over 22,000 miles above Earth, but an unmanned rocket's second stage misfire left it stranded. Melnick and his crew were tasked with capturing it, attaching a new second stage, and sending it on its way, a mission that demanded precision and courage. As the countdown neared zero, the shuttle's 3 liquid-fuel rocket engines were about to ignite, powered by turbopumps drawing fuel from the massive external tank slung beneath the orbiter. Meanwhile, the 2 colossal solid rocket boosters, the largest ever built, remained dormant, waiting for their moment. When the signal arrived, confirming the main engines were ready, an inferno would erupt within the boosters, igniting the solid rocket fuel and propelling the revolutionary reusable spaceplane into orbit. This was the intricate and awe-inspiring engineering of the space shuttle, a marvel of human ingenuity. With minutes to go, the shuttle was fully fueled and operating under its own power, disconnected from the launch pad. Helium and nitrogen had purged the main engines, and the flight surfaces and engine gimbals had been tested. At 10 seconds before launch, sparkler-like igniters fired beneath the engines to burn off stray hydrogen as the main fuel valve opened. Liquid hydrogen surged through the fuel lines, driven by tank pressure, and began expanding into gas as it passed through the engine nozzles. This gaseous hydrogen powered a low-pressure turbopump turbine, accelerating the flow. In less than a second, the main oxidizer valves opened, unleashing the fuel's full potential. Fuel and oxygen met in high-pressure turbopumps, boosting flow rates further. Initial flames appeared in the nozzles, but low oxygen levels caused combustion instabilities, making the engines rattle. Soon, the engines transitioned to open-loop control, monitoring pressure and adjusting valves dynamically. The orange flames shifted to an eerie, hot blue as oxygen valves opened wider and the engines throttled up. Unlike traditional rockets, the shuttle's main engines were offset from the fuel tanks, attached to the reusable orbiter rather than the expendable external tank. This design caused the shuttle to twang when the main engines ignited, bending the structure as it strained against the solid rocket boosters, which were anchored to the launch pad by hold-down posts. These posts, connected to the booster's aft skirts by massive 711 mm long, 88 mm wide bolts, prevented the shuttle from tipping over. The bolts were secured with frangible nuts, designed to explode on command. On 2 occasions, some nuts failed to fracture properly, a issue NASA called stud hang-ups. While 1 or 2 misfires didn't halt a launch, 4 or more could have been critical, prompting a redesign for later missions to ensure simultaneous detonation within 50 microseconds. As the main engines reached 90% thrust, the solid rocket boosters ignited. Each 45-meter-long booster was packed with a rubbery solid fuel mixture, 70% ammonium perchlorate oxidizer and 16% aluminum fuel. Ignition began with a miniature solid rocket motor, itself sparked by an even smaller one, shaped with a 40-point star orifice to maximize surface area and ensure rapid combustion. Safety mechanisms, including a pin in the booster's top skirt, prevented accidental ignition. At T-5 minutes, technicians rotated the safety device, connecting a NASA detonator to the igniter system. Once ignited, the boosters unleashed 13,000 kilonewtons of thrust each, nearly double that of a Falcon 9 first stage lifting the shuttle off the pad. Solid rocket boosters were a bold choice for human spaceflight, previously used mainly for military applications like the Minuteman ICBM. Unlike liquid engines, solid boosters couldn't be throttled or shut off once ignited, burning until all propellant was consumed. To manage this, the booster's fuel column was shaped strategically. The upper section featured an 11-pointed star cavity, maximizing surface area for high initial thrust, which decreased as the points burned down. The lower section transitioned to a tapered circular cavity, reducing thrust by 33% 5 seconds into flight to limit dynamic pressure. The boosters were filled in pairs to ensure consistent fuel batches, minimizing differential thrust that could veer the shuttle off course. Steering relied heavily on the booster's nozzles, which provided 80% of control via hydraulic actuators in the aft skirt, allowing pitch and yaw adjustments. 7 seconds after liftoff, traveling at 140 kilometers per hour, the shuttle initiated a roll program. Asymmetric thrust vectoring rotated it 180 degrees and pitched it 12 degrees off vertical, aligning it with its orbital trajectory. This maneuver, necessitated by the launch pad's Saturn Vera design, reduced stress on the wings and gave the crew a view of the horizon. At 45 seconds, the shuttle broke the sound barrier, and the roar of the engines faded, replaced by the howl of air rushing over the shuttle's thermal tiles, sounding like a train in a tunnel. As the atmosphere thinned, even this noise dwindled, leaving a rough, quiet ride as the boosters neared depletion. 2 minutes into the flight, lowering chamber pressures triggered the booster separation. If sensors failed, a timed backup system took over. The nozzles returned to neutral, and the orbiter held its attitude for 4 seconds. The boosters were attached to the external tank at 4 points, secured by frangible connections. 8 separation motors, 4 at the top and 4 at the bottom, fired, each delivering 96,000 newtons of thrust to push the boosters clear. The sudden bang of explosive bolts and the fireball from the motors startled Melnick on his first flight, briefly making him think the shuttle had exploded. The boosters climbed to their apogee, then deployed parachutes from their nose cones for a controlled ocean landing, where they were recovered and reused. The shuttle, now in its second stage, relied on its 3 main engines, fed by liquid hydrogen and oxygen from the external tank. This tank, a structural backbone, connected the orbiter and boosters, bearing immense loads. At 47 meters long and 33.5 metric tons empty, it was a reinforced aluminum thermos flask, insulated with 2.2 tons of orange foam. The liquid oxygen tank, smaller due to oxygen's higher density, sat atop the larger hydrogen tank to raise the center of gravity above the center of pressure, ensuring stability. A load-bearing inner tank with a massive internal beam resisted compressive forces from the boosters, while the lower attachment handled shear stress. Liquid oxygen flowed through a 46 centimeters wide pipe, equipped with anti-vortex baffles to prevent instability from swirling fluid. Both fuels traveled through umbilical plates to the orbiter, with gaseous lines maintaining tank pressure to prevent structural collapse. Main engine cutoff occurred at a velocity of 28,000 kilometers per hour, or when depletion sensors detected low fuel levels. Extra hydrogen ensured a fuel-rich shutdown to protect the reusable engines. Frangible nuts separated the external tank, which tumbled away, venting oxygen to avoid recontact. Closing the orbiter's umbilical doors was critical for re-entry. Failure would require an unthinkable spacewalk. Fortunately, this never occurred. The tank, the only non-reusable component, broke apart during re-entry, its pieces scattering into the ocean. Melnick's first task as a rookie was to photograph the tank post-separation to check for anomalies, but, overwhelmed by the sight of Earth, he nearly forgot, capturing only a distant image as it fell away. The shuttle's design balanced ambition and compromise. Initially envisioned as fully reusable, budget constraints and Air Force requirements led to the expendable external tank and larger cargo bay.